Welcome back, Calculus. We are on section 1.2b, limit properties. I'm going to force a pause on your screen. You know what to do. Okay, I'm actually going to force another pause on your screen. Go ahead and copy what's on my page, and then we'll work these together. Okay, so for example 1, we've got two functions, and this time they're defined graphically. And what we're going to do today is properties of limits. So we're going to add, subtract, multiply, divide, and compose functions within limits. Okay, so for this first one, we've got the limit as x approaches 0 of f of x plus g of x. And as long as the two limits exist separately, we can just find the two limits separately and then add them together. Okay, so let's try that. So I'm going to draw my guide at x equals 0 for both. So, and I can tell that the full limit's going to exist for both, right? So if I approach from the left and the right here, I can tell that the y value is approaching 0 for f. And if I come over to the function g and I approach that wall from the left and the right, I can tell that the y value is approaching what number? It's approaching, or actually is on 1, right? So now I can just add those two together, and my final answer is 1. All right, so let's try the second one, the limit as x approaches 2 of f times g, right? So if I draw my guide at x equals 2 for both f and g, and see that the full limits don't exist. Now, we can't just jump to conclusions and assume that this limit isn't going to exist either. What happens with functions is that they can be better together. So any idea what we can do here? For the full limit to exist, what has to be true? The left and the right hand limits have to equal each other, right? So what we're going to do is split this into two problems. Find the left hand limit, find the right hand limit. If those are the same, the full limit exists as well. Okay, so let's try this. So let's start with the left-hand limit. The limit as x approaches 2 from the left of f of x times g of x. All right, so let's approach those guides just from the left. So coming from the left here, what is my y value approaching? It's approaching 4, and I'm going to multiply. Now coming from the left to g, what's my y value approaching? It's approaching 1. So my left-hand limit of f times g as x approaches 2 is 4. Okay, now let's try that coming from the right. So the limit as x approaches 2 from the right-hand side of f times g. Okay, so I'm going to come back to function f, this time approach that wall from the right. What y value are approaching coming from the right? We're approaching 2. Now if we do that same thing, approaching this guide from the right, I can tell that my y values are also approaching 2, and 2 times 2 is 4. Okay, so does the full limit exist? It does exist, and the full limit as x approaches 2 of f times g is 4, since the left and the right hand limits were both 4. So I'm going to force another pause on your screen. You don't need to copy the graphs, they're the same, but I want you to now copy the two new limits I have on the left-hand side. So can you tell what kind of operation I'm looking at now? So both of these are composition. They've got one function inside another, right? These are not multiplication, okay? So notice if it were multiplication, it would be f of x. G of x. We read this as f of g of x, not f times g of x. So these are compositions. Do we work compositions from the inside out or the outside in? We work compositions from the inside out. So let's take a look at that first limit. We've got the limit as x approaches 1 of f of g. So which graph do I want to look at first? F or g? We want to look at g of x first, okay? So I'm going to take the limit as x approaches 1 of the inside function. So let's find this. Let's draw our guide. So the limit as x approaches 1 of g of x is 1. So it's 1, okay? So whatever that limit answer was, that becomes my new input, okay? So this is going to become the limit as x approaches that new value, which was also 1, of just f of x. So I've already taken care of the inside part. Okay, so now let's move over to f of x. Find the limit as x approaches 1 here. Let me be careful. Okay, then I think we get 1 as well there for that limit. Okay, I know I did not ask you to do this, but let's take a similar look. Let's take that same composition, but this time try the limit as x approaches 0 of f of g of x. Okay, so I'm still going to start with my inside function, still starting with g of x. So now I want to take the limit as x approaches 0 of that inside function. So if I draw my guide here, the limit as x approaches 0 of g of x is what? Looks like that's 1, okay? So that now becomes my new limit. So now I take the limit as x approaches what? 1. So remember, what was your output now becomes your input with compositions. So of just f of x. So now if I find the limit as x approaches 1, we found that earlier, right? Of f of x, that is equal to 1. Okay. All right, let's try that last one on this page. So this time, what function are we starting with, f of x or g of x? This time we're starting with f of x. Always start with the inside function, right? So I want to find the limit as x approaches -2 of g of f of x. So let's go ahead and draw our guide. So as I approach -2 from the left and the right, the y values approach 4, right? So now this becomes the limit as x approaches 4 of just g of x. I've already taken care of the inside piece, okay? So now I'm going to come over to the g of x graph. As x approaches 4, the y values here approach 2. All right. So for example 2, you don't need to write down what I have this on the screen right now, but just write what I write in ink. So it says find two functions, f and g, such that the limit as x approaches 0 of f plus g is 5, but the limit as x approaches 0 of f of x and the limit as x approaches 0 of g of x do not exist. Okay, so if we look at these functions separately, there's a jump right as x approaches 0 for both f and g. But if I combine them, if I add the two, then the limit now does exist, and we want the limit to be 5. Okay, so here's what I'd like for you to write. Let's first start. We're going to go ahead and give these graphs analytically. You could also give them as a graph, and I'll show you what they look like as a graph as well. But let's start by defining two functions, f and g. And now what I'd like for you to do is think of two numbers that add to be 5. Okay, I'm going to use 2 and 3. Okay, so I know that I want my split to be at 0. So we're going to have that top piece be x is less than 0, the bottom x is greater than or equal to. Doesn't matter where the equal sign is, right? Because that's the function value. So we said 2 and 3. So what I'm going to do is put a 2 for the y value here and a 3 for the y value there, right? So now when I find the left-hand limit of f plus g, it would go 2 plus 3, which is 5, right? Now, let's flip it for the bottom piece. Let's do 3 and 2. Okay, so now when I find the right-hand limit of f plus g, I'd have 3 plus 2, and that's also 5. However, notice that the limit as x approaches 0 of f, the full limit doesn't exist, right? Because coming from the left, you're at 2. Coming from the right, you're at 3. Similarly for g of x, the left-hand limit is 3, the right-hand limit is 2, so the full limit doesn't exist. But when we put the functions together, when we add them, the full limit does exist. Let's take a look at the graph. All right, so on the screen, I've got the graph of f. So you can see that my y values are 2 for all x's less than 0 and 3 for all x's greater than or equal to 0. Now let's show the graph of g. So that's going to look like the opposite of that, right? So here's f and g together, or graphed on the same axes. Now here's f plus g. Ah, that looks nice, right? So now I can see the full limit of that green graph does exist, even though when I looked at just the red or just the blue, the limit did not exist at x equals 0, right? But when I added them together, now I've got this nice limit that exists at x equals 0. So for example 3, I'm going to force a pause on your screen. Go ahead and copy this and attempt it, and we will talk about the solution in class. All right, so the last thing I want to look at is called the squeeze theorem, also known as the sandwich theorem. And it says this: so if you've got functions f, g, and h, and they have the property that for all x in an open interval containing c, but maybe not at c, that g is squeezed in between the functions f and g. So you can see, like in the graph on the right here, that g is this red function, and f is the concave down parabola, h is the concave up parabola. So g, in this case, is squeezed or sandwiched between the other two functions. Then, if you've got that the limit of f as x approaches c and the limit of h as x approaches c is equal to the same number, well then the function that was squeezed between the two also has to be equal to that number as well. Okay, so I'm going to force a pause on your screen, copy my screen or whatever you need from my screen, and then we'll go ahead and do one question together. All right, so here is an example of the squeeze theorem. Again, I'm going to force a pause on your screen. Go ahead and copy my screen, and then we'll work this together. So it says, use the squeeze theorem to find the limit as x approaches 0 of g of x, given that g of x is between negative x squared and positive x squared. Okay, so if, let's say the graph was given, we could see, okay, yes, that is definitely approaching 0, right? But let's say we don't know what g of x is. We just know that it is squeezed between these other two functions. Well, then what I do is I apply that limit, the one I'm trying to find for g, to the other two functions, and we hope that we get the same answer, okay? So here's what we're going to do. We're going to take the limit as x approaches 0 of this function, negative x squared. Well, if I plug in 0 for x, what do I get? It's 0. And we're going to do the same thing to this function. So the limit as x approaches 0 of x squared. And again, when I plug in 0 for x there, I get 0. So now, by the squeeze theorem, because g of x is between negative x squared and x squared, and you do not have to state this theorem, but if you do state a theorem, you have to state the right one. So by squeeze theorem, the limit as x approaches 0 of g of x is what? Is also 0, because these guys were 0 and g of x was squeezed in between those two. Okay? All right, as always, put any comments or questions in the assignment box, and I'll be sure to check on those, and we will follow up with this and check the challenge problem in class. See you then.